Well, okay. Good morning, everybody. This is Vijay Garg. I'm at UT Austin. It really gives me a lot of pleasure to introduce our next speaker, Professor Jeff Ullman, who hasn't read books written by him. But in any case, he is at Stanford. He's at Stanford. He's the professor in the Department of Computer Science. He received the BS degree from Columbia University in 1963 and PhD from Princeton in 1966. Prior to his appointment at Stanford in 1979, he was a member of technical staff at Bell Labs from 66 to 69. From 1990 to 1994, he was chair of the Computer Science Department at Stanford. Okay, he has received all the awards you could think of. He was elected to NAE in 1989, American Academy of Arts and Sciences in 2012, National Academy of Sciences in 2020, Guggenheim Fellowship, Einstein Fellowship. He has also received Sigmod Contributions Award 96, Karlstrom Outstanding Educator Award 98, Knuth Prize 2000, EF Cord Innovation Award 2006, IEEE von Neumann Model 2010, NEC C&C Foundation Prize 2017, and ACM Turing Award 2020. He's author of 16 books. I have used many of his books, and it's a real pleasure to introduce him. Jeff, please, you can start the presentation.
Well, thank you very much, Professor Gahn. Okay, I think you should see on your screen sort of the menu for the next hour or so. I want to talk about MapReduce algorithms, obviously. I assume everybody by now is familiar with the idea. I'll just run through the ideas very quickly so that you have also that we have the terminology set. And then I want to talk about an example of a design problem for MapReduce algorithms that actually came up in a course I was teaching about, I don't know, a dozen years ago. And the interesting thing is it's not the kind of problem that would come up if you were designing a serial algorithm or a conventional parallel algorithm. It's sort of unique to the MapReduce world. And this actually led to a theory, and it involves these two concepts called reducer size and replication rate. I will, of course, define these, and the trade-offs between them that sort of limit what you can do as a MapReduce algorithm. And then I'm going to just very briefly run through a couple of MapReduce algorithms for problems, Hamming distance, that is finding bit strings that differ in only one bit. The multi-way join, this is a database operation that, again, I'll give you the definitions if you are unfamiliar with them. And matrix multiplication, I'm going to assume everybody knows what matrix multiplication is. Okay, I want to thank the people who worked with me along on these the topics that I'll talk about: Fadil Afradi, Anishta Sarma, Semi Salyaglu, and Shantanu Sharma. Okay, so again, as I assume everyone is familiar, MapReduce is a system. Hadoop, of course, is the it was at the time we did this work the popular embodiment of the MapReduce idea. Now it's I guess it's all Spark. Spark has a little bit more than MapReduce, a lot more than MapReduce, but MapReduce is still the operation that gives Spark a lot of its power. So what you get from MapReduce is we can write algorithms that run in parallel, even though you don't have to think about parallelism. It automatically manages failures of compute nodes in the whatever computer environment you're operating in. But the fact is, you have to give up something. That there is, it's a subtle limitation on what you can implement using MapReduce. Not just any old parallel algorithm runs works in the MapReduce environment. So as I said, I'm going to talk about what these limitations actually are and talk about some optimal algorithms, really optimal family of algorithms, because there's always a trade-off between these two concepts of reducer size and replication rate. Anyway, we'll get to all of that. Okay, plug for a book. It's free, so I don't feel guilty at all about mentioning it. It does have an extensive chapter on the concepts that I'm going to talk about, and you can find it at the link given here, www.mmds. That's Mining of Massive Datasets.org. Okay, so here's what MapReduce is all about. Okay, you start with a collection of inputs that have a single type, although in fact, many interesting cases, that type is a union type of really disparate objects. And then the programmer writes a map function, and this map function is applied to every input using whatever parallelism, if any, is available in the system. Now, I want to use the term mapper to mean the application of the map function to a single input. Now, in practice, you have many mappers. That is the map function applied to often thousands or millions of inputs at once. They're grouped into a map task, and the map task is sort of the unit of parallelism, but that turns out not to be all that important in this theory. Okay, then the map function is written so that in response to any input, you get some number, could be 0 or 1, or lots of key value pairs. Key value pairs are of a new type. Okay, then behind the scenes, the programmer doesn't have to touch this. The system will take all the key value pairs that are generated by all the mappers, and it sorts it sorts the key value pairs by key, and then forms all the values associated with a given key into a single object that is a list of values. Then the programmer is writing another function called the reduce function that takes key list of values arguments and produces objects of some other type. So I want to, okay, one application of the reduce function to a single key and its list of values is called a reducer. This turns out to was very important in the theory. But in practice, many reducers will be grouped into a single reduce task, and the reduce task is the unit of parallelism. Okay, and as I said, so each reducer will produce some output, and the output of the MapReduce job is the union of what each reducer produces. So here's sort of the pattern. You first feed each input to a mapper, and so you've got all these mappers operating with as much parallelism as you can muster. In principle, any mapper could produce output for any reducer. I've shown sort of a complete graph here, but in practice, and in fact, that's sort of how the way you design good algorithms is arranging that each reducer receives output from relatively few mappers. Okay, now, obviously, an important cost of a MapReduce algorithm is the total execution time for all of the mappers and reducers. You can't control the work behind the scenes to sort everything by key, sort the key value pairs. And this essentially is the rent you pay to the cloud service that you're running on. But there's also a hidden cost, which is the communication cost, which you also pay for if you're renting machinery. And that is the communication cost of transmitting output from the mappers to the reducer that each output belongs to. Remember, each reducer corresponds to a key, and the mappers are producing key value pairs, perhaps with different keys. Now, I'm going to assume that you're using lots of compute nodes so that essentially the chances that a key value pair is generated by a mapper and it will run on a reducer that's at the same compute node is essentially zero. So I'm going to just count, I'm going to assume that every time every key value pair needs to be moved and therefore incurs a communication cost. Now, for some algorithms, not all of them, this communication cost is actually greater than the cost of the execution time of all the mappers and reducers and the sorting that goes on behind the scenes. I'm going to give you an example in a second. And so this is, I just want to go through this example. I think it will give you, I hope, an idea of where the problems come up. Okay, and again, this happened actually many years ago now. A course that we teach on it's a data mining project. Many of the projects use MapReduce. The particular project that I'm going to talk about did in fact try to use MapReduce, running on AWS. And the students actually contrived this project themselves, and it turned out very well, although there was, let's say, a nervous moment in the middle where things just did not seem to be working. So the students were working in the medical school, and they had data for 3,000 of drugs, which is half of all the drugs that the FDA has approved for use. By the way, so they had lots of data, and for each they had a period of 20 years, the patients that took the drugs, when they took them, what diagnoses were made, what conditions the patient suffered, and so on. Now, of course, it varied by drug, but on the average, a drug had about a megabyte of data associated with it. Okay, so the total data set, 3 gigabytes, right? That's not all that much these days, but it's not insubstantial. Okay, and anyway, the research problem that the students adopted was to try actually to find drugs that when you take them together, they increase the risk of you having a heart attack. And by the way, just to give you a scale, there are 80 such known drug interactions, or there were at that time. When they did their analysis, they discovered 40 of them were in the data. It's very possible that that's all that was in the data, because of the other 3,000 drugs that were not in their data set, I assume that many of the interactions involved at least one of those drugs, so they had no way of seeing that. They also found two cases that were not known and had very high chi-squared numbers. So it's very likely that these were unknown drug interactions. Okay, now, the fact is that the only sensible way to do this, unless you have a magic wand, is you have to look at each pair of drugs, perform a chi-squared test on them, and see if taking both of them together increases your risk of heart attack beyond that which you would expect from taking one of the drugs separately. So let's see, it was time for midterm review, and the team implemented an algorithm with the following idea. Again, the inputs, of course, will be the 3,000 inputs, the 3,000 drug records. And so the mapper is going to generate a key consisting of a set of two drugs, let's say drug I and drug J. And the value will be the record for one of those drugs. In particular, the drug that this mapper has as input. Okay. So in particular, what the map function is going to do is if it's given drug I and its associated record, say R sub I, the mapper will generate all the key value pairs of the form. The key is I and J, that is I is the given input, and J is any of the other drugs. And the value will be Ri, which is, of course, the only input that it has as a value. Now, when you look at the situation from the point of view of the reducers, the reducer for the key ij is going to get the record I from the mapper, the record Ri from the mapper for I. And it's going to get the record Rj from the mapper for drug J. And that's all it's going to get. So that's what the key list of value pairs looks like. So I want to give you a little picture of this process, I'm going to assume 3 drugs rather than 3,000 because my slides just aren't that big. So here's the mapper for drug 1. The first thing it does is it generates the key 1, 2. 2 is, of course, one of the other drugs besides 1. And the value will be the drug 1 data. Then it generates also the key 1, 3, 3 being another drug besides 1. And attaches to that the value, again, the drug 1 data, which is the only thing that the mapper for drug 1 has. And then in parallel, the mappers for drug 2 and 3 are doing the analogous thing, producing all the keys. For example, mapper for drug 2 produces the keys 1, 2, and 2, 3, and the drug with the drug 2 data and so on. Then, behind the scenes, all of these key value pairs get sorted. And, for example, the 2 generated key value pairs with the key 1, 2 get sent to the reducer for 1, 2, and so on. And then things are organized in the proper format for a reduce function, which is the key followed by the list of the associated values. So for example, the reducer for 1, 2 gets the key 1, 2 and the list of the 2 records for those 2 drugs. And its job now is really to do a chi-squared test on these 2 values. And again, in parallel, reducer for 1, 3 and for 2, 3 doing the same thing. Okay, so that seems simple enough. Well, again, I said this was the day before the midterm reviews were due, and I get this nervous email saying we've implemented the algorithm, we know it works, but we sent it off to AWS, and it's been a day now, and nothing has come back. Well, look at it this way. There are 3,000 drugs. And if you look at what the algorithm is doing, for each drug, each mapper is generating 2,999 key value pairs. That is, its drug paired with all the other drugs. And then the key value pairs it generates is about a megabyte long. So you multiply all that together and you get about 9 terabytes. And these have to be communicated over 1 gigabit, sorry, Ethernet. Well, it's a little trickier because they're running on AWS. There are lots of connections, each of which maybe carries a gigabit. But so maybe you can get some parallelism in the communication, but you're also competing with other jobs that are being run on the same hardware at the same time. So it's not clear how many, just how much communication you can get. But the bottom line is that you need about 90,000 seconds of network use. That's a little bit over a day if you're doing the math. So it's kind of no surprise they weren't getting anywhere. So we had a little conference, and the team then decided to re-implement the algorithm, and here's how they did it. They first grouped the drugs into 30 groups. So you had 100 drugs in each group. And now their keys would not be pairs of drug numbers, but pairs of group numbers. So there would be only 30 times 29 divided by 2, or 30 choose 2 different keys. That's a much more reasonable, tractable number. You see, they were generating so many different keys, they didn't have anything like that number of cores to execute all of those in parallel anyway. And even, what is it, roughly 400 and some odd keys with this new design, they didn't have 400 machines anyway. So they're still getting all the parallelism they could possibly get. Now, the mapper for drug I produces 29 key value pairs. The keys would be the set containing whatever group I is in. There's a number of the group for drug I, and any of the 29 other group numbers. Okay, and the value is still basically the megabyte long record for drug I. You do have to tag it with telling what drug this actually is the record for. You didn't have to do that in the original design because it actually didn't matter. Each key each reducer knew what pair of drugs it was getting. Now, from the point of view of the reducers, so the reducer for a pair of groups, say group M and group N, will get the 200 drug records corresponding to the 100 drugs in group M and the 100 drugs in group N. And this reducer has to compare, and that is do the chi-square test, basically 10,000 chi-square tests, each record from group M compared with each record from group N. And there's a small matter if you still have to compare records for drugs in the same group. So when we had some arbitrary way of assigning that job to one of the 29 reducers that would get the records for a particular group, not important. Now the computation is still the same. You're still comparing, running a chi-square test on every pair of drugs somewhere, and you're only doing it once. So you're doing the same amount of computation. Okay. The win is that the communication is much lower. Now you have still 3,000 drugs, but for each drug, you're only replicating it 29 times rather than 2999 times. This gives you 87 gigabytes of communication. Right, it's gigabytes of communication. Still not an insubstantial amount, but they were able to get their job done in a few hours of computation time. Now, based on this one horrible example, I guess we developed a theory, and I want to really just go over the elements of that theory. Okay. Well, the first thing is we started with an abstract model for MapReduce problems. Okay. Every such problem, you're given a set of inputs, such as the 3,000 drug records, and you have a set of outputs. That is the things that you want computed. In this case, in our example, the output would be for each pair of drugs, you want a bit saying this is a drug interaction or a bad drug interaction or not. And then, without reference to exactly how, let's say, how a chi-square test works, we know that there's going to be a many-to-many relationship between the outputs and the inputs that are needed to compute that output. So, for example, no matter how you group the drugs or don't group them, the output associated with the pair of drugs I and J requires the inputs for drugs I and J, and it absolutely requires those, and it requires nothing else. So here's a picture again, assuming there are 4 drugs rather than 3,000. So there would be 6 outputs. 4 choose 2 is 6. So, for example, the output for the pair of drugs 1 and 2 requires drug 1 input and drug 2 input, but doesn't require drug 3 and drug 4. Okay, so this sort of a picture is the abstraction of an algorithm, and it's the thing that's going to let us say you can do just this well, but no better. Okay, so here's another example: matrix multiplication. Now, this isn't the whole diagram, but rather for any of the let's say if this is n by n matrices. So there would be n squared outputs, each of which looks like this. So the output for the element in row I and column J requires the whole row I of the first matrix and the whole row, the whole column J of the second matrix, but nothing else. Okay. Now, again, the first element of the theory is what we call reducer size. And I'm always going to denote it by Q, and it will always be gold colored in these slides, I hope. So, okay, so it's the maximum number of inputs that a given reducer can have. That is, it's an upper bound on the length of the value list for that reducer. So for one, you might pick Q just so that whatever is being done by the reducer can be done in main memory, because that will make the code actually run much more efficiently. Or you might make Q artificially low because you want the algorithm to have lots of parallelism. And it's the computation, total computation may be the same, but it can be, the wall clock time can be reduced if you force there to be lots of parallelism. And then the other member of this this trade-off is the replication rate, which we'll always denote by a blue R, and it's the average number of key value pairs that are created by anyone by a mapper. So it's essentially the communication cost per input. So let's see how we can, let's look at this, the drug interaction problem and see how Q and R are related. Well, in general, let's assume that there are D drugs. Again, in the example I gave, D was 3,000. And we use G groups, some number of groups. In the first algorithm, G was 3,000, and the second, G was 30. So you have D divided by G drugs per group. And a reducer, again, required two groups. So the reducer size Q would be 2D over G. Now, each input is going to be sent to G minus 1 reducers. That is the reducer for its group and the other groups. And again, I'm going to assume that all these numbers, D and G and R and Q, are large. So G minus 1 and G are pretty much the same. So just to make things simple, I'm going to assume that the replication rate is G. It's actually G minus 1, but let's just call it G. Now, okay, if we accept that R and G are the same, then in this formula, I can replace this G by R. And then I like to flip the Q and the R. It's the same, it's really the same equation. The reason is Q is something you can control. When you design the algorithm, you determine how big the reducers have to be. And R, the replication rate, is a consequence. So, so this formula, R equals D over 2Q, says that for any Q, there's an algorithm with a replication rate that is 2D over Q. So this is a trade-off. What it says is the bigger you make the reducers, the less the communication costs will be. Now, what that says is you have an upper bound on the replication rate, but maybe you can do better. Right? That's just we just gave you. I gave you one family of algorithms. So what I wanted to show is that, well, more or less, you can't do much better. Let's put it that way. And so we need a lower bound on R as a function of Q. So in order to get such proofs, you need the notion of a mapping schema, which is essentially an abstraction of a MapReduce algorithm. Okay. So again, so a mapping schema for a given problem and a particular reducer size Q assigns each input to sets of reducers that it says for each input, where does the mapper send that input? And it has two requirements. One, no reducer is assigned more than Q inputs. That's the definition of reducer size, really. But the important point is that for every output, there has to be some reducer that receives all the inputs that are needed to compute that output. Okay. And so we're going to use the term covered. So the reducer covers the output. And see, this is the nature of MapReduce algorithms. If an output isn't covered by any reducer, then no reducer gets the stuff it needs to compute that output. And therefore, this mapping schema is not going to work to solve the problem. Okay, so my point is that every MapReduce algorithm has to have a mapping schema, in particular a schema that satisfies that second condition. And I think that this is the thing that makes MapReduce algorithms different from serial algorithms or let's say parallel algorithms run on a random access machine of some sort. So let's again go back to the drug interaction problems and try to get a lower bound on R. Okay, so again, I'm assuming there are D drugs. reducer size is Q. Now, no matter how we do it, now there's no notion of groups yet, but I know that each drug has to meet D-1 other drugs at some reducer, right? So if you send the drug to a particular reducer, then there can't be more than Q-1 other drugs at that reducer, because that's the limit on how much input the reducer can get. So therefore, I have to send each drug to at least, this one, the ceiling. Okay. The ceiling of D-1 over Q-1, that is, this is how many drugs it has to meet. This is how many it can meet at one reducer. So this is the number of reducers. Oh dear. Okay, I should not do that anymore. I don't know why that happened. Okay, so what this says is the replication rate is at least this formula. And again, since I'm assuming D and Q are large, it just says R is D over Q. Now, if you remember, the algorithm, the family of algorithms that I just talked about had R equal to or less than, actually equal to 2D over Q. So it turns out that the lower bound is really pretty much precise. That is, you can get almost down to D over Q, okay, using a more complicated algorithm than the one that I gave you. I'm not going to discuss that here. Now, I want to talk about another example. In the example I just gave you, what you had was R, the replication rate is inversely proportional to the reducer size. That turns out to be a very common situation, but it's not universal. And in particular, the reason I want to talk about the Hamming distance 1 problem is that that here, it turns out that the replication rate is inversely proportional to the logarithm of Q, the reducer size. Okay, so again, the problem is we're given a set of bit strings of length B, and our goal is to find all the pairs of bit strings that differ in exactly 1 bit. Okay, formally, the notion of the Hamming distance of the strings is 1. So a simple example, if the length of the string B is 2, there are 4 strings shown here, 0, 0, 0, 1, and so on. And there are 4 outputs. 0, 0, and 0, 1 are of Hamming distance 1. These 4, for each of these 4 pairs, the 2 strings are distance 1. The pairs that aren't outputs are things like 0, 0, 1, 1, because they have Hamming distance 2. So again, the theorem is that the replication rate in the optimal algorithm, that upper and lower bound, is B over log base 2Q. Well, first of all, the smallest that Q can be is 2, right? Because each output takes 2 inputs, so Q equals 1 can't do anything. On the other hand, we could create a reducer for every pair of inputs that are at distance 1. And you'd have a replication rate of B, because each bit string of length B will be set to the reducer. The reducers correspond, or the keys will generate key value pairs with the key that is that string and any of the B strings that differ in exactly 1 bit. Okay. Now, again, from the point of view of the reducer, it sees, does it get both of the strings that it's looking for? Again, one or both of those strings might not be in the input, so the reducer doesn't get all that it needs. If it gets both inputs, then both strings, then it outputs, yes, this is a pair. Otherwise, it does nothing. Well, on the other extreme, we could basically have a serial algorithm. And there you need Q is 2 to the B because there are 2 to the B bit strings. So we're going to send all the bit strings to one reducer. That is, there's only one key. Okay, and all the mappers do is they take their inputs and send it to this one reducer. So there's no replication at all. So R is 1, and basically there's one reducer, it does all the work. So it's really a serial algorithm. Now here's an algorithm that's a little bit more subtle. I'm going to just to make life simple, I'll assume that B is even. And I'm going to associate reducers with strings of half the length, that is length B over 2. And for each string of length B over 2, there'll be 2 reducers. I'm going to call them the left and right reducers for that string. Now, if I take an input W of length B and break it into a left half of length B over 2, that's X, and a right half of length B over 2, that's Y, I'm going to send W to the left reducer associated with X, because that's the left half, and the right reducer associated with Y. Now, if 2 strings, say W and some other string Z, differ in exactly 1 bit, then they both get sent to the left reducer if the bit in which they differ is in the right half, or they'll be sent to the same right reducer if they disagree in the left half, but not both. So now each reducer looks for the strings that it gets that differ in exactly 1 bit and outputs them. So now the replication rate is 2 because each string gets sent to 2 different reducers. And the reducer size is 2 to the B over 2 because, let's say, a left reducer can get 2 to the B over 2 different strings. That is, they have the same left half and all possible different right halves. Now, okay, again, well, it's an example of upper bounds. I want to get the lower bound on the replication rate. And there's a general technique which we're going to apply here. The first thing is, and this is typically the hard part, is you need an upper bound on how many outputs a reducer of size Q can cover. And this is the thing that requires thinking for each problem. But once you have that, you can take the total number of outputs and divide that by this upper bound that gives you a lower bound on how many reducers you need. Then you can okay, if you know how many reducers you need, you multiply that by Q, because that's the number of inputs that each of the reducers will get. That gets you a total number of inputs to all of the reducers. And that therefore is a lower bound on the total communication. And then to get the replication rate, that's the total communication divided by the number of inputs. Now, there's a tricky point, which I don't want to go into, but it turns out if that upper bound that you get in step 1 is at least linear, and it kind of always is, then you can assume that an optimal algorithm will use as few reducers as possible, each of which gets as many inputs, that is Q inputs, as many as possible. Okay, now I'm going to give an outline of the proof that R is lower bounded by B over log 2Q. Now there's a lemma which is a little bit tricky, which is the thing that says how many outputs can a reducer of size cover? And again, that turned out to be Q over 2 times log base 2Q, and it's an induction on B, the string length. I'm not going to get that. Now, the number of outputs that need to be covered is b over 2 times log b. Why? Well, for each of the 2 to the b different strings, there are b strings of distance, Hamming distance 1, but if you add that up over all strings, you're double counting each pair, so you have to divide by 2. So the number of reducers you need is at least this number divided by that number, which is simplified here. And then taking over all the p reducers, the inputs to those reducers is p times q, which is just this formula with the q taken out of the denominator. And then the replication rate is PQ, that's this formula, divided by the number of inputs, which is 2 to the b, and that gives you b over log base 2q. So this is r is at least b over log 2q. So here's the lower bound. And well, the first algorithm I gave you, we have one reducer for each input that has a replication rate of b, and 2 to the first power, or 2, as q, and then the trivial serial algorithm has q is 2 to b and replication rate of 1. And then the splitting algorithm has replication rate 2 and 2 to the b over 2 as a reducer size. And you can generalize splitting instead of 2 groups into 3, 4, 5, and so on. So you get points all along this curve. Interesting thing is we were never able to get a similar lower bound for Hamming distances greater than 1. Still open. Now, I want to talk a little bit about this problem of multi-way join and how to do that using MapReduce. And again, I assume most people are going to be familiar with the relational model of databases, but just in case anybody wants a review, first, a relation is simply a table with names for the columns, which we're going to call attributes. The column names are called attributes. That turns out to be important in what I say. So I want to give an example. The relation is called likes, and it has 2 columns, drinker and beer. And each row tells about some drinker and a beer that they like. And you assume each drinker likes many different kinds of beer. So, but I'm going to talk about one particular row, the row Fred and Budweiser, which means that the drinker Fred likes Budweiser, possibly among other beers. Now, another relation I'm going to call frequents, and it has 2 columns, the drinker and the bar. And a row like Fred and Joe's bar says that Fred sometimes at least visits Joe's bar. And then another relation serves bar with columns bar and beer. And by the way, relations can have more than 2 columns, but in our example, they just have 2 columns. Again, what this means is that the bar serves this beer among others. So for example, there might be a row that says Joe's bar serves Budweiser. Okay. Now, a key database operation is joining relations. And this is actually called the natural join. It's not the most general case, but it'll do for now. And the idea is, if you're given relations, you want to join them. Well, first of all, what you get is a set of tuples or rows, and the rows have the columns or components correspond to all the attributes that appear in at least one or more of these of the given relations, and the requirement to be a tuple in the join, the result, is that for each of the relations, there's a row that agrees with the output tuple in whatever attributes it has. So for example, we could join the three relations on the previous slide, that is likes, frequents, and serves, and you would get a tuple like this. For example, the frequents relation has drinkers and bar as its columns. And if you remember, I said one of the rows is that Fred sometimes frequents Joe's bar. So you're good. You've got that tuple in these two components. And then serves relates bars and beers, and I said that Joe's bar serves Budweiser. And then finally, likes has the drinker and beer columns only, and I said that Fred likes Budweiser. So everything fits together. You would get Fred, Joe's bar, Budweiser as one of the outputs in this join. Now, if you look at how a real database system operates, what it's always doing is it's finding linear order in which to do the join. So if you're given three or more relations to join, you pick two to join first, and it's an interesting optimization problem as to which two to start with and the order in which to join them. But you join two relations, now you have a new relation as an output. You join that with another relation that gives you, again, a new intermediate result. And then you keep just joining relations until you've joined them all, and that gives you the result. Now, in many times this is best, where you'd use it if you're using MapReduce. You'd use one MapReduce job to do a join. And if you think about it, MapReduce was almost perfectly designed to do join of two relations. But it turns out that when you're joining three or more relations, sometimes you're stuck with the intermediate results have to be much larger than the actual result. And the bars and beers and drinkers is a perfect example of this. And it's possible to then run a single MapReduce job that joins all the relations. The cost is you actually have to replicate rows of the relations more than once, which you don't if you're doing a cascade of two-way joins. But again, because you never have to deal with these huge intermediate results, it turns out to be a win. Okay. So how you would design the a multi-way join is, what we're going to do is we're going to take, first of all, the attributes that appear in more than one relation are the critical ones. The ones that appear in only one relation, they just sort of get carried along and they're not important. So I'm going to assign for each attribute appearing in more than one relation a share, which is the number of groups into which its values are partitioned. And the product of the shares for all of the attributes then will be is the number of reducers. And that might, let's say, we want to limit that to some reasonable amount. So that question becomes then, what should the share be for each attribute? So in our example, each attribute appears in two relations. So a reducer would correspond then to a group for each attribute. So there'd be a reducer would correspond to one bar group, one beer group, and one drinker group, and there'd be one reducer for all of those combinations. And the trick is the rows now have to be replicated. They're sent to all the reducers for groups to which the row belongs. So for example, the row Fred likes Budweiser is sent to all reducers that have the group for Fred, because we know if this row could only participate in combinations involving that group. And the reducer also has to have the group for the beer Budweiser, but we don't know about the bar just seeing this row. So we have to send it to all the reducers that have the group for Fred, the group for Budweiser, and any of the bar groups Okay, and so the replication rate for this particular row, the number of times you replicate this row, is equal to the share of the bar attribute. So it turns out the number of times you replicate a row is the product of the shares for the attributes that the relation does not have. In this case, the example I just gave you, it would just be the only attribute it doesn't have is bars, so it would just be the number of shares of the bars. So it turns out to be optimizing shares is a tricky optimization problem, but you can do it. And the intuition is you want to give small shares to attributes that appear in the smallest relations, so that the big relations don't get replicated a lot. The rows of the little relations may get replicated many times, but that's okay because there aren't that many rows. You want to make sure that you don't replicate the big relations too much. Okay, and again, you can't make all the shares be one because you want to have some product that's bigger than one. So you have to give some share to some of the attributes anyway. Okay, I wanted to finish up by just mentioning a little bit of the story of matrix multiplication. It's an interesting story because it's a case where we can actually prove that a 2-round MapReduce algorithm is better than a 1-round MapReduce algorithm. Okay, so the problem with that is multiply n by n matrices, assume that they're dense matrices. And again, I'm just going to throw out the numbers for you. They're not that hard to do. A reducer size Q can produce only this formula, Q squared over 4n squared outputs. Now, if you run through that formula for getting lower bounds, what you get is that R is at least 2n squared over Q. So this is another case where replication rate and the reducer size are inversely proportional. And then since there are 2n squared inputs, what you get is a 4n fourth over Q as the total communication. And again, let me just say the obvious tiling algorithm where you break the matrices into squares will pretty much match the lower bound. Interesting thing is you get, I think it's 6% less communication if you use tiles that are aspect ratio 2, that is, they look like dominoes rather than squares. But that's not all that important. Well, it turns out that there is a 2-round matrix multiplication algorithm that uses less communication. It's 4n cubed over square root of q. Now, I should comment, there's no point in making q much bigger than n squared. So square root of q is presumably less than n. And therefore, to the degree that square root of q is less than n, 4n cubed over square root of q is less than 4n fourth over q. Okay. So I think that's it. A couple of open problems. This is interesting because we haven't really found other algorithms where you can actually prove that 2-round MapReduce will give you less communication than a single round. And then another interesting problem is we've never really been able to get anything about lower bounds for communication of even algorithms that use two rounds of MapReduce, 2 MapReduce jobs. Okay, and with that, we'll take some questions if there are any.
Okay, first of all, I want to thank Mr. Ullman. And any questions for him? So I had a question. You talked about lower bounds and upper bounds in MapReduce model. Is there any work which relates bounds here to bounds in parallel computing? You said these problems are a little bit different, but is there
Yeah,
some...
because I mean, if you, let's say on a PRAM, let's say as a general model of parallel computing, you don't you don't have a notion really of replication rate or reducer size, right? I mean, there's no, you've got one memory. It's everything.
Yeah.
Okay. Yeah. So neither of those concepts really make sense in a PRAM world.
Okay. Any other question for him?
Yes, I would like to ask about data lakes. Now there is a notion of data lakes. Is there a relation to MapReduce, and what are the opportunities there?
Yeah. I don't know. What do you think, Shlomi? No idea. Maybe I don't know. Maybe an interesting question. But I honestly don't have.
We have a student. We have a student that started working on data lakes. Maybe we can communicate about this data.
Well, yeah. I mean, again, I'd have to see how this theory applies, but it could be whenever you have a restricted form of parallel computation, you might have a theory. I don't know if how many remember the theory of integrated circuits, area time squared bounds. Okay, again, that's an integrated circuit is another parallel. It's a way of doing parallel computing that has some funny constraints on it. Okay, and it gives you this unique area trading off with the square of the time. Again, that makes no sense in a MapReduce world or a PRAM world. I presume in a data lake world, but who knows? So yeah, I'm happy to talk to you about that.
Yeah, data lakes is a matter of money because they use very cheap storage. This is the issue. So there is another opportunity to look
it's
at.
It's all a matter of money, Shlomi, but hey, what the heck? Yeah. Okay. Yeah. No. I'd be interested. If the student's getting anything, or if you're getting anything, that's. Yeah, I mean, it could be.
Yeah. Okay.
Any other questions?
I have one more small question here. So, hello, Professor. How are you?
How are you doing?
Yeah, I am good. Thank you. So, my question is related to MapReduce and machine learning. So, do you see anything that one can do in use MapReduce for machine learning purpose?
Well, again, given that given that machine learning is all about matrix multiplication, it would be interesting to look at it. I think the trouble is here, matrix multiplication is so essential in the machine learning world that you use specialized chips.
Yeah, GPU.
So you have the GPUs and there are other things as well. So you get yet another theory. Again, GPU is another constrained environment. So it's not likely that the theory that we worked on many years ago from MapReduce, it's not likely that carries over in an interesting way to the world of GPUs or TPUs or in any of these other any of the other architectures that people are now talking about as accelerators for computation in general.
Okay, thank you.
Any other question?
In fact, I know Shantanu, I know that you have worked on these data vaults, right? Those are limited size chips that protect data. That may be another
Yeah.
theory
Yeah, yeah. Mm-hmm.
of these.
Mm-hmm.
Okay, if there are no more questions, let's thank Jeffrey again. And I'll
Thank
hand
you for
it back.
listening.
Wonderful talk. Elad would take it back now.